Hello, this is Pete Cachopi. I'd like to give you a brief talk today regarding building prescriptive analytical solvers with Python. So let's start by orienting ourselves a little bit by discussing the overall range of tasks for which people often use Python. So at one end of the spectrum, we have things like exploratory programming. This is where you would just fire up a Python interpreter like IPython and then load up some data, load up some libraries, analyze the data using the libraries that you've loaded, maybe do some trial and error code to learn more about your libraries. All of those are reasons why Python is a great language for data analysis and also just an easy language to learn. Python also allows for something that's almost unique to Python, which I like to call demonstrative programming. So specifically, I'm talking about launching Jupyter, creating a Jupyter notebook, which is a file that can be shared over the internet, and that file can contain text and graphics and actual functional code. So it's sort of like a file that has some rich comments and effectively records what you would do in an IPython session. Um, so moving closer towards the production world, we have things like glue programming. This is where you can use Python to move data from one system to another. So Python is very useful in things like integrations for that reason. So with respect to prescriptive analytics, Python is a good tool for rapid prototyping. So for example, you might have a business problem and a set of data that demonstrates an instance of that business problem, and you're wondering whether mixed integer programming could work well to solve that problem, or perhaps constraint programming is a good fit, or perhaps some combination of heuristics and optimization is a good fit. And so in order to determine what could run efficiently, what could work well, you write a series of Python scripts that just execute different solution strategies against your data sets. So that's what I would call rapid prototyping. Now, as your rapid prototyping matures, you would build something that I call mature code. So this was code that's easy, that's ready to be deployed. And one of my thesis here is that making code deployment ready is often consistent with making code that's easy to share or making code that's easy to archive. So for all three of those uses, code that's robust for deployments, code that's easy for a new person to understand and easy to recover, you want code that's self-documenting, code that's self-validating, and code that clearly defines how it's supposed to be used. So specifically, how do you go about doing that? Well, I've prepared a checklist that describes the characteristics of a mature solver. I've organized this checklist from sort of the most general to the most specific. So at the top, we look at things that you would expect from any piece of mature Python code, regardless of whether or not it's executing prescriptive analytics or some other environment, some other domain space. Typically in Python, what you do is you organize your code into a package. So a package is the Python name for a library. Python provides the packaging infrastructure to allow you to easily specify what parts of your code are publicly available and what parts of your code are used to implement sort of the inner workings of what you're trying to do. A package is itself usually archived and shared in a repository. So this is sort of just a file structure thing. The package directory is usually the child directory of a repository directory, and that allows you to put other ancillary information or additional files, descriptive files, that sort of thing, can go into the repository sort of outside of the package directory. And we'll look at specifically what that means in a minute when I walk through a specific package that I've built for demonstration purposes. Python, it's also expected in Python that you incorporate testing into your mature project. So by this, I mean people that build Python packages and share them in repositories also include automated testing that can be used to exercise the code in the package. So generally, the repository has a testing section that has script files that launch the code in the production section. Now, in our case, for prescriptive analytics, this dovetails nicely with the requirement that as you build more and more sophisticated engines, you will quickly see the value of having a test suite for your engine, right? So it's really, if you have a very complicated engine and you want to share it with somebody, it's natural that you're going to want to share sample data as well. It's also the case that as your engine evolves over time, as you add features to that engine, you want to make sure that new functionality doesn't break old functionality. And so for that reason, it makes a lot of sense to build a test suite to accompany your engine. And that test suite requirement maps almost perfectly onto the incorporated testing requirement that's part of Python in general. And we'll talk about, and again, we'll see that more specifically when we walk through the repository that I've created as an example. So moving into things that are specific to mixed integer programming or to analytical programming, prescriptive analytics can generally be thought of as building a solve engine that takes a specific data instance and determines whether or not that data instance can be met feasibly, and if so, it creates an optimal or near optimal solution and returns that solution. So I think there's a good distinction that can be made here between prescriptive analytical engines and the libraries that prescriptive analytical engines call. So for example, mixed integer programming is more of a general purpose type of engine, right? Constrained programming is also more of a general purpose type engine or a library. So you don't think of mixed integer programming or constrained programming as solving on specific schemas. But the engines that use mixed integer programming almost always do solve on specific schemas. So if you look through, for example, the example code in Gurobi or the example code in Cplex, those examples are designed to solve specific problems that have specific schemas. My point here is that what makes good sense is that you specify the solve function that runs that takes a given schema as an input and returns a given solution that matches an output schema. And along with that solve function, you should publish the schemas themselves. So by this, I mean you should make your solve function self-documenting, right? So you could do this with comments, although what I recommend is that you use the tictat library so as to programmatically define your input and output schemas. So tictat is a library that I'm going to be showing you the particulars of in a little bit. Tictat is an open source library that we at Operalytics have created for the dual purposes of promoting good solver development and also as the API for people that want to deploy solvers as applications on the Operalytics cloud platform. So it's sort of a case of benevolent self-interest. We've turned the API for the Operalytics cloud platform into an open source public library that is hopefully useful for everyone. So what can you do with tictat? Tictat allows you to publish the input to clearly define input and output schemas. It also allows you to define data validation rules that are associated with those schemas, and I'll walk into the specifics of that in a little bit. But by defining the data validation rules, then it allows the solver to be self-validating. So not only will your analytical engine be self-documenting in that it explicitly presents the input and output schemas, it'll be self-validating. And then if you give the solve function an improper input data set, it'll give you an intelligent error message instead of merely throwing a strange exception or quietly returning bad data. Now, the final and most sort of picayune bullet point that I want to discuss here is that I think it makes good sense to follow a consistent pattern for representing data tables within Python. So to that end, tictat supports two styles for representing a data table. You can represent a data table as a dictionary of dictionaries, or you can represent a data table as a pandas data frame. So for those of you not familiar with pandas, pandas is a library that's built to facilitate tabular analysis. It's a much bigger and richer library than tictat itself. So tictat sort of can be thought of as living on top of pandas or taking advantage of pandas instead of replacing pandas. Um, in my experience, pandas is the right data library for doing machine learning type of analysis, for doing statistical analysis. But when you're writing mixed integer programming code, most people, I think, are similar to me in that they like to see the code laid out as iterating over indices and capturing slices of subtables that match parent tables or vice versa. So if you think of, and this is the way you would write code, this is the way people write code in the modeling languages that are sort of mixed integer programming specific. So, and it's also that sort of coding style of iterating over indices and finding subslices of data is also most consistent with the way mixed integer programs are written out when they're just written out as mathematically in LaTeX. So for those reasons, I encourage people to use dictionaries of dictionaries as the representation of tables in Python. And I think TICDAT has a lot of has done a good job of supporting that representation. However, people that want to use pandas data frames are certainly encouraged to do so. And just to explore the sidebar a little further, I've put several pandas examples of mixed integer programming on the TICDAT example section, and I honestly think I'm the only one doing that. I think I'm the only one who has presented rich example code of, okay, suppose I have a data set that has multiple tables and has foreign keys. Suppose it's a data set where you would naturally use slicing. I want to use pandas instead. What does that look like in actual pandas code? And I think if you look over those code examples, you might end up agreeing with me that dictionaries of dictionaries makes more sense. But choices are good, so TICDAT gives you choices. So let's jump into the specific code here, and let's look at a repository that I've put online to allow as a demonstration project for the bullet points that I've just discussed. So I actually have two projects that are online that meet that mature solver checklist. One is example diet, and the other is example netflow. Both of those are based on Gurobi examples. So let's just walk through the diet example here, and then feel free to go on to the Opolytics GitHub site and look at both the diet example and the netflow example. So here we have our repository. In GitHub, the repository renders nicely so that the README file, looks pretty. This is the root directory of this repository would be example-diet. Now let's explore the file structure a little bit. So this directory here is the package directory. So this repository is implementing a directory implementing a package called diet. You can tell that the diet is the package directory because it has the init.py file. The init.py file can be left empty, but I encourage you to actually populate that file with the code that specifies what are the public parts of the package. So in particular, at a minimum, the public parts of your package should be the input schema, the output schema, and the solve function. If you also want this, and the solve function takes an instance of the input schema and returns an instance of the output schema. Now, if you also want to make utility functions that allow you to directly read and write from Excel files or from CSV files, instead of solving from data structures, if you want to write utility functions that solve from files, it's fine, go ahead and do so. I think if you look over the TICDAT example code, you'll see how TICDAT, once you've written out this basic structure, once you've got the solve routine written correctly and the input and output data factories written correctly, it's actually just a few lines of code to actually then connect that logic to files on your system. Now, briefly, this is the testing section. So in this case, we have a very simple testing section. So we just have one testing script. This is the testing suite. So this is where I'm storing my data for the testing section. And in this case, I only have one data instance, so I only have one data file. I'm storing that data file in a file format that's somewhat particular to TICDAT. So these are valid SQLite statements. but they don't execute the schema. They only populate the data. And the reason being that once you've specified the schema through TICDAT, TICDAT will automatically create the schema statements for you. So that's one of the advantages of TICDAT. I find it much easier to work with these other file types through TICDAT than if I were to try to use the file libraries directly. So it's much easier to use TICDAT. If you look at the TICDAT code, you'll see TICDAT is just a layer on top of the SQLite library, the CSV library, the XLS library, and the ODBC library. I would strongly encourage you, regardless of what you think about my opinions of modularity, I think you'll agree that it becomes a lot easier to read and write data through a more high-level library like TICDAT than through the low-level libraries that are native to Python. Now, I'm just going to briefly discuss the testing script. If you want to learn more about the testing script, I encourage you to study this testing example. There's another one for NetFlow, and also to study the documentation for this unit test library. So I think what I'm presenting here is somewhat unique. I don't think there are any other public demonstrations out there of how do I use the unit test library to implement a test suite in Python. I think I'm the only one showing that. And I think if you're at all feeling ambitious, I don't think it's terribly hard to actually create something like this yourself just by following my example. If you want to go that route, I would also encourage you to look at this notebook that I have up here in the Explore section that shows you how to create that SQL file from a real-world data instance, for example, from an Excel data sheet or from an Excel data file. Now, I also should point out that if you've gotten to this point of the talk and you're saying, you know what, this testing section, this building of the automated testing, that's not the part I'm interested in, well, that's one more reason for you to become a client of Opolytics, because we are excited about testing, if you can be excited about such a thing. And so in the same way that we're excited about rapid automating the process of building GUIs, we're also excited about facilitating the building of test suites. And so if you're just really focused on doing the mathematics and you want to sort of outsource the testing to us, as you also outsource the building of your GUI and the deployment of your engine, that's fine. That sounds like a happy business arrangement for everyone. Oh, before I finish with testing, I should note one more thing. If you study Python, you'll often, a more common way to organize the repository is to put the testing section up here. So to have that testing folder be a sibling folder to diet instead of being a child folder to diet. I like to organize it this way because it makes it easier for me when I'm doing exploratory programming within IPython. I want to easily get a hold of the test suite. So I find that common task is facilitated by putting the testing section inside of diet. But if you're worried about doing it, it doesn't matter a whole lot. It's just a matter of being a little bit unusual for the sake of creating a convenience. Okay, so now at long last, we can look at some specific code of doing the sexy part. This is the code that's doing the math. So as you can see, this is a Gurobi example. So I'm importing Gurobi, and I'm using the TICDAT library to import a factory and the freeze_me function. You don't have to worry too much about freeze_me. You can study that in the documentation if you want to see what that's about. The TICDAT factory is the base object that you use to define a schema. So for example, when I'm creating a TICDAT factory object here, what I'm doing is I'm defining a schema. What is this schema? I'm defining the schema. It has 3 tables, and here are the fields for each table, right? So there's the fields for categories, there's the fields for foods, and there's the fields for quantity. So this is sort of the equivalent of building a data access, it's sort of the equivalent of building an access database that has only tables and fields and no data. And what I'm also doing is I'm organizing the fields into 2 groups. The first grouping of the fields is the primary key fields, and the second grouping is the data fields. So for example, the categories table has just a single primary key field and 2 data fields. The foods table has a single primary key field and a single data field. The nutrition quantities table is a child table, and as such, it has two primary key fields with 1 data field. Now, what's happening here is this section and this section are both technically optional, but I really encourage you to follow the full template here, right? So what I'm doing here is I'm specifying how the nutrition quantities table um, is meant to function as a child table of its two parents, right? So the nutrition quantities table should match up to the foods table with the food field matching to the name field. And similarly, the nutrition quantities table should match up to the categories table with the category field matching the name field. So essentially, by defining this child-parent relationship, it gives truth to this code down here, right? This code checks that the foreign keys are valid. So in other words, this code here is checking that the food field and the food field and the category field are all valid, right? That's a good thing to know. You don't want to run a solver with invalid fields. So it makes sense to check the validity of your field values before solving. And so your fields are either, if your fields are supposed to match up through a child-parent relationship, then you can specify that relationship with the add foreign key function here. And for your data fields, what makes sense is to specify a data type. So that's what this code here does. By the way, TICDAT is well documented online, so I'm going a little bit quickly, but that's because I'm encouraging you to dive into the documentation or contact me as you prefer. So what this code here does, it's saying that all the data fields have the default data type, which is non-infinite, non-negative number with no integrality requirements, except for max nutrition, which allows infinity, right? There's no upper limit to certain types of nutrition. So in order to achieve that, we just say that inclusive max is true and that the max value is the infinity value. So now that we've defined the input schema, the next thing to do is to define the output schema. There's no real need to define the data rules on the output schema because your solve function is going to be creating instances of the output schema. In this case, you could argue that this is the only table that the output schema really needs. For this particular problem, once you've specified the quantities of food to purchase, you've really specified the solution in full. But I think it's valuable to provide ancillary tables with ancillary information. So here we're also describing how much nutrition is consumed for each category. And there's also a parameters table that has a single field. It's intended to have a single value. And that's the parameters table. And for this example is where you would store the total cost of the solution. So as you might have noticed, this is an example of how you define a table that has data fields but no primary key fields. And if you look at the NetFlow example online, you'll see the example of the inverse of that, of tables that have primary key fields but no data fields. Now let's move on to this solve function. This solve function is about 55 lines of code or so, 45 lines of code. I encourage you to look at Gurobi's webpage and to compare the Gurobi example to the solve function here. And the lesson I'm trying to impart by encouraging you to perform that comparison is that you can think of the Gurobi code as being basically equivalent to a rapid prototype. And this is the production code. So the lesson I'm trying to impart is that it's really not that difficult to use TICDAT to upgrade your rapid prototyping example into a production code example. Now, that said, I've done rapid prototyping and gone directly to TICDAT, and I think that works just fine as well. So I don't see any reason to skip out on TICDAT at that stage. I mean, I've used TICDAT for every stage of those initial bullet points. I've used TICDAT with exploratory programming, with demonstrative programming. I guess I haven't used it with glue programming yet, but I've done all the other points. That said, if you want to think of TICDAT as something you bring in once you're trying to achieve the production code stage, that's also a valid use of TICDAT. So since you've already studied the Gurobi example and you understand that example, I'm not going to spend too much time going blow by blow through this code since it's so similar to the Gurobi code. I would just like to point out a few things that are specific to TICDAT. So again, we've talked about these 3 lines. These are the lines of code that validate the input data. So in this case, you could think of the input as being sort of the conceptual equivalent of an access database. So this line of code would then validate that the correct tables and fields are present. This line of code validates that the child tables match up correctly to the parent tables. And this line of code validates that the data fields all pass your basic sanity checks. Now, as I talked about before, a data table in TICDAT is represented by default as a dictionary of dictionaries. So that's what's going on with something like this line of code. Again, this represents the equivalent of a database. This is a table in that database which renders in Python as a dictionary of dictionaries. So items is a dictionary function that allows you to iterate through the keys and the values of a dictionary. Each one of those values is itself a dictionary. The inner dictionaries are keyed off of the data field names. So the categories table has a min nutrition and a max nutrition field. So those two fields are the keys of all the inner dictionaries. Similarly, the foods table only has one field, a data field, and that's why the inner dictionary here just has one key, which is the cost string, the name of the single data field. Here we are referencing the nutrition quantities table as a dictionary of dictionaries. So again, this is the equivalent of a database. This is like a table in the database. This looks up the row in the database table that matches food equals F and category equals C. And this looks up the quantity value for that row. So again, this perhaps it might look a little scary at first, but if you're going to be doing this type of work, again, I really think you should standardize around one of two ways to represent tables. And I think you'll find this ends up being the simplest way for mixed integer programming. So this bottom section here is if the solution is successful, if the optimization is successful and you're returning a solution. So the first step there is you create a solution TICDAT object that's consistent with the solution factory. So this is sort of the functional equivalent of creating an access database that has the right tables and fields, but doesn't have any data rows. And then the code here is where you're populating the data rows. So I'm just going to deep dive into that code just a little bit because there's some TICDAT overrides there. I want to make sure everything is clear. So this is the most laborious, but also the most easily understood way to write back the data. So since this is a dictionary, the way to add an entry into the dictionary is to refer to look up a specific key for that dictionary as the left-hand side of an assignment, and that way Python will create that value if it's not present. So here we are creating a row for the table. And since that row is itself supposed to be a dictionary, then here is the data row. And it's indexed by the fields of the data table. Now, if this looks a little tedious, if always having to have the right-hand side be a dictionary when you're adding data rows, you can also TICDAT also has the overrides that allow you to write it this way. So this statement here is sort of, first when TICDAT executes a statement like this, it recognizes that it's going to need to add this data row in order to set this data value. Now, if the by food table had more than one field, then when you're adding a data row just to set one of those fields, the other fields would take on the values of the default values for that schema. And I haven't shown you default values. That's another part of TICDAT that you can explore. I find default values to be useful. Some people don't like them so much. But if you want to write code this way, you'll often end up taking advantage of default values, and they're easy to specify in TICDAT. Now, for this particular output schema, the by food table and the consume nutrition table only have one data field. So for that, TICDAT is also smart enough to recognize that this bit of code is optional. There's really no need to specify the data field that you're writing into if there's only one data field. And that's what's happening here. That's why this code doesn't refer to the quantity field at all, because it doesn't need to. There's only one data field. Okay, so I think that covers all the main points. Hopefully you enjoyed this talk, and feel free to contact me with any questions.